Odors are something we encounter every day: the smell of fresh coffee, a blooming rose, or lemon. For decades, scientists assumed that each odor produced a distinct, reproducible pattern of neural activity in the brain. However, more advanced recording, such as multi-neuron arrays and EEG, revealed a surprising reality. The responses are noisy, highly variable, and often overlap for similar or weak odors. Noise disrupted the neat pattern assumed by classical models, making fixed pattern approaches unreliable and inconsistent across repeated exposures. So what is the solution? The manifold hypothesis offers a way to make sense of this variability. Although hundreds of neurons fire simultaneously, creating a high-dimensional space, the meaningful variation created by an odor is confined to a low-dimensional structure embedded within that space, the manifold. For instance, plotting the activity of just two neurons against each other over time shows that, despite fluctuations, points tend to follow a line that captures the main relationship. Deviations from this line reflects noise rather than meaningful signal. Scaling up to hundreds of neurons in the olfactory cortex, the raw high-dimensional data becomes a messy, almost uninterpretable cloud dominated by variability. Dimensionality reduction techniques, such as principal component analysis, PCA, solve this problem. PCA identifies the direction along which data varies most, those reflecting the consistent odor signal, and projects the high dimensionality points onto these axes. Random fluctuations in noise, oriented along less important directions, are largely ignored. The result is a smooth trajectory along the manifold that preserves the signal while suppressing irrelevant variations. Through this framework, the brain can reliably encode odor identity. Rather than reading exact patterns of neuron activity, it can interpret odors based on the shape of the trajectory along the manifold. Noise is effectively filtered out, highlighting the essential relationship between neurons and showing that population-level dynamics rather than individual neurons carry out the critical information.